Good morning, everybody. My name is Kevin Renaud with Peerless. It is 11 o'clock, but we are seeing a bunch of people still piling in through the doors. So we're just going to wait another minute and we will get started. Good morning again. This is Kevin Renaud with Peerless, and we're going to get started here. This is now week 6 of our e-learning initiative. Thanks for joining us. Today it's why pressure instruments fail and how to mitigate these failures with REOTEMP. So in typical fashion, I'd like to go through the brief introduction, then just change it over to our presenter. Today's geography, again, is quite diverse. I think new to the group is Indiana. If your state's not reflected here, I do apologize. We did have a lot of late entrants, and I may not have had a chance to update it. We also have a lot of different industries represented: chemical, engineering, OEMs, skid builders, manufacturing, and education. So briefly, Peerless, today we're a trusted source for process components that keep plants operating safely and efficiently, and projects running smoothly and on time. Our customer base is diverse, skilled, and quite complex, and we're certainly proud of the role that we play. Our business group is made of 3 different segments. Procore, we deal primarily with the OEM customers, engineered equipment and packagers, and we then have our process group, which is chemical, pharmaceutical, contractor, power, food and beverage, manufacturing, and of course, universities and government. And finally, our high temp division, which is a fabricating component to our company where we work with high temperature insulation, refractory, scientific surfaces, and laboratory medical equipment. Today, our presenter is Justin Kloss. He is from REOTEMP. He's the regional manager. Mark Leonelli could not join us. They are conducting an ISO audit right now, and he's stuck wrapped up in that. From the Peerless side of things, we have Dan Morgan, our continuous improvement manager. He also heads our engineering team. There's Greg Barrow, business development for our process group. And there's me, Kevin Renaud, business development. So in typical fashion, this introduction could get boring to those of you that have been with us for week after week, and we do appreciate that. I like to just briefly talk about something specific to the presenter. And Justin Kloss is also a marathon finisher. I'm starting to get sick of asking people for accomplishments because this is now the 2nd or 3rd time that someone's finished a marathon. But he did beat his goal of 4 hours. And just so you know, I do my fact checking. I did find that he was at the starting line. It's tough to see that, but more importantly, it's the finish. So I was also able to capture his photo at the finish. So, and he sure does look great. I don't know how he does it. Good form. He looks fresh as a daisy. So with that, congratulations on that, Justin. And I'm going to hand it over to Dan Morgan, who will be moderating today's session, and he'll just go over some of the housekeeping. Thanks again for joining us.
Yep, thanks, Kevin. Thanks again, everyone, for joining us. For those of you that are new, just to explain a couple of things, there is a questions pane that you can see in the control panel of your interface here, and you can absolutely feel free to use that to ask questions at any point during the presentation. I'll be keeping an eye on things, any questions that come through, and I'll be finding points to interject into Justin's presentation to make sure those questions get asked and answered. So please feel free to ask away through there. The other thing we're going to be doing, just want to mention real quick, is we're going to run a couple of polls throughout this to sort of test test, I guess, Justin's skill in presenting and teaching you this information. So you'll see a couple of points today throughout the presentation. We'll throw a poll up, and there's a chance you may need to exit out of full screen mode if you're in full screen mode in order to click into or participate in the poll. So that's just one thing to look out for. So with that said, I will now turn this over to Justin.
All right, good morning, everybody. My name is Justin Kloss, as Kevin said. I'm with REOTEMP Instruments. That's a great picture of me there, Kevin. It was a great run and a good finish. Today, we're going to be talking a little bit about protecting your pressure gauges. What are some of the reasons that your pressure gauges fail, and some of the reasons, or some of the things that we can do to combat that. We'll get started here. Pressure gauges, they need a protection. A little bit about the pressure gauge. Your pressure gauge is going to have more moving parts than most of your other instrumentation in the piping system. I don't know how many of you are familiar with what the inside of a pressure gauge looks like. There will be some pictures a little later. You can kind of get a somewhat of a good idea, but they're almost like a watch internals. They've got small gears, small springs, and small linkage that all kind of work together to move the needle when there's pressure applied. So a lot of moving parts inside of a pressure gauge, more than most of the other instrumentation in your piping system. Your pressure gauge is going to have the lowest max working pressure of any instrument in the piping system. Typically, you know, if you've got 100 psi gauge on there, your overrange pressure is going to be 130 psi. Most gauges have a 30% overrange capability, which means you can overrange it 30% without damaging the gauge or without shooting it off into space. If you start getting higher than that, there is burst pressures and stuff like that tell you your max capability. But typically, the pressure gauge is going to have a lower max working pressure than any other instrument on your piping system. The process media, it does get inside of a pressure gauge. It is going to go up inside the board on tube. It will go inside the connection, inside here, and inside the housing. There is going to be a board on tube inside here, which we'll see a little bit later. The process media does get inside of there, so it's unprotected from any chemicals or anything like that as it stands alone. This also may be the cheapest instrument in your piping system. You've got valves and pumps and regulators and other parts on there that are going to be a lot more expensive than your pressure gauge. Your pressure gauge may cost $100, maybe less than that, depending on what style you have, but it is going to be the cheapest instrument in the piping system. And then the board on tube is going to have the thinnest wall in the system as well. It's a small metal tube that's curved like a C shape, and it is going to have the thinnest wall. It's only a few millimeters thick versus the rest of your piping system that could be a lot thicker. What killed the pressure gauge? There's a number of factors that can come into play when a gauge is not working anymore. One of the first things could be overpressure. This is typically done during a startup or shutdown. During startup or shutdown, pumps may kick on and shoot a surge of pressure through the system. A valve might not be open or might get opened at a certain time when the pressure is built up and that pressure shoots through the system. And if that pressure hits the pressure gauge, it may spike and it may kill the internals of the pressure gauge. Vibration is going to be the second one. Vibration could happen if the gauge is mounted on any kind of a motor or rotating equipment that's causing a lot of vibration. You guys are pretty familiar with how a car motor works. Those things are shaking constantly. If you put your hand close to it, you're going to be able to feel it. Same thing with a pressure gauge. If you've got something on there, it's going to sit there and shake, and those fine internals of the gauge are going to get destroyed. Pulsation, this is caused by any pumps or valves. If you've got like a diaphragm pump or a piston pump or something like that that's constantly pulsing the pressure line, that gauge is going to see all that pulsation as it goes through that line. And then heat, if there's any heat, whether it be the process fluid is too hot, or if there's any nearby equipment, whether it be a furnace or a kiln or something like that that's real hot, you could possibly melt the gauge or cause damage to the internals. And then corrosion or clogging. This could be caused by the process fluid. If it has any big particulates in it, it could cause the gauge to clog up and not operate properly. A little bit more about overpressure. If a gauge does get overpressured, there's a couple of visual indicators of the failure. One is going to be the pointer does not return to zero. What happened, or the pointer could get bent or fall off, or If it does get bent, what happens is the gauge is swung all the way around and it came back around and hit the pointer stop. A couple of visual signs on the inside here, or internal indicators. The board-on tube here, you'll start to see it swell up like a balloon. This is caused by overflexing the board-on tube. This may not be a leak in the gauge, or it may not cause the gauge to come off or break or anything like that, but you will see this start to happen and the gauge isn't going to read properly. When this happens, you're flexing that C tube too far, and then the pointer's not going to return to zero. This here on the right is your normal operating tube. You can see it's a real nice, clean, smooth bend. This one's here more ballooned. And then if the pointer does get bent, or if it does swing around too fast and hit the pointer stop, this little control arm right here gets bent a little off, and that's an indicator that we can see that that the gauge has failed. Some of the solutions for overpressure: you can increase the range of the gauge. Increasing the range from a 0 to 200 psi gauge up to a 0 to 300 psi gauge buys 50% more protection at the cost of only plus or minus 0.5 psi accuracy. If you increase the range, you're going to get a lot better. You may lose a little bit of the accuracy, a little bit of the clarity on the dial, but you are going to protect the gauge and not have to replace gauges on a regular basis. The second option is adding a pressure limiting valve, also known as an overload protector. Basically what happens is the pressure, you install this between the pressure side, the process side here, and then you've got your instrument mounted on top of here. And as the pressure goes in the one side, there's a spring inside of here with a little valve. If that pressure gets too high, it'll close off the pressure to the gauge. So if you've got a 0 to 100 psi gauge on there and you set the valve at 100 psi, once that valve, or once that overload protector hits 100 psi, it's going to shut the valve, limiting the pressure to the gauge. The gauge is going to stay at 100 psi, but the pressure on the process side may be 200, 300, 400 psi, depending on what your process is. And then once the pressure starts to reduce or starts to decrease, the valve will open up. Once it gets to 100 psi, it'll start to open up, and it'll relieve the pressure, and you'll see the gauge start to drop down. So then you're still getting your good accurate reading. These are good for startups. If you know that the system's going to spike, you can throw one of these in. That way you know that the pressure gauge is working, but you're still protecting it and keeping it from seeing the high pressures. Another option is a needle valve or block and bleed valve. You can install one of these with your pressure gauge, close the valve off before you do your startup, and then once you do your startup and everything's in normal operating conditions, open the valve up and a pressure gauge will read without causing any damage or over spiking it. Dan, did we have any questions here?
Nope, nothing yet.
Okay, we will move on. We're going to go into pulsation. So pulsation, like I mentioned before, is caused by a pump that could be spiking the pressure pulsation through the line. Some of the visual indicators of a failure: the pointer does not return to zero. If you've got your pointer and it comes, it's up, normal operating PSI is 200, you turn the pressure off and it comes back down and it's at 50 PSI, there's an indication it could be pulsation. If the pointer is falling off, that pointer will tend to be hammered constantly up and down. The pointer could fall off just from the vibration of it doing that. The pointer, if it is bent upon impacting mechanical stop, same thing with overpressuring it. If it pulses too high and it comes around and hits the mechanical stop, could cause damage on the internals. And another indication is the dust or powder would build up inside the case. It could get so bad that you will see it on the dial, you will see it on the glass on the inside of the case. Or when we take it apart, we can look inside and see that. Internal indicators of failure: the pinion gear, the gear inside of there could be worn down. Adjustment screws may have come loose, so there's a little adjustment screw on the front of the dial here. If that comes loose, then there's going to be an issue. Or if the overload stop shows impact marks where the needle's constantly banging against it and pitting the overload stop. This here's a little video of, on the left, we've got a pressure gauge here mounted to just a typical snubber. And then on the right, we've got a pressure gauge mounted to REOTEMP's Pulse Clutch with Pulse Plus, which I'm going to talk about a little bit in the next slide. But I'm going to go ahead and play this video real quick here. You guys can kind of take a look. So they both have the same pulsation applied to it. You can see this is going to beat up a gauge over time, especially if there's small gears on the inside. The one on the left has a snubber, which is one of the solutions, which, as you can see, mitigates it a little bit. But the one on the right is with our Pulse Plus, and that's going to do a little bit more. a little bit better on the pulsation protection. We'll go here to the next page where we can get into some of the solutions. One of the solutions is assuring that there's a restrictor screw inside the gauge. This tiny little screw here is going to go inside the process connection here. And what that does is it has a much smaller orifice than the pressure gauge itself does. And that limits the amount of pressure that can go in and out. And that's going to mitigate the pulsation a little bit. That's going to be your first step. If you've got a minor amount of pulsation, that's going to be your first step in is using one of those. Most of our PR series and PT45 series, which are all stainless gauges, have restrictor screws in them. And then some of our PG series, our stainless case brass internal gauges, are going to have restrictor screws in them as well. The second option, as you saw in the video on the one on the left, is going to be a snubber here. What this does is one style is it's going to have a screen right here. That's going to restrict the flow of the pressure going through that, and it's going to mitigate the pulsation on the gauge. As you saw in the video, we were hammering that with an air hammer, which was pulsating it quite a bit. A snubber is used in most common cases, simply because it does a pretty effective job at minor pulsation. You know, if you've got a pump way down line or something like that, a snubber might be good. Anytime you're going to have heavy pulsation, where a snubber, as you can see, didn't do the trick, REOTEMP has what we call our Pulse Plus option. It's a pressure gauge mounted on a diaphragm seal. We embed a snubber in between these two, in between the diaphragm seal and the pressure gauge, and then we use a thicker fill fluid. And what that does is that thicker fill fluid going through this restriction causes that pressure to slow down even more when going through there. It's going to combat the pulsation, the heavy pulsation, a lot better than the other two options. And the only thing you sacrifice is a little bit of response time. It's a minute amount of response time, but if it is something you will see. But what that's doing is it's slowing the pressure going in and out of that gauge down, so you're not damaging the gauge. You're getting a good accurate reading on the needle, and you're able to protect the gauge and make it last a lot longer. Dan, any questions on this one?
We do have a question. It's potentially a little bit of a spoiler alert. I know what's coming next in the presentation, but in case anyone else out there is wondering the same thing, the question is, will a liquid filled gauge help with pulsation?
I think this should move us into our next slide. What do you think?
Yeah. Do you want to maybe launch a poll quick to see how everyone's, or should we wait one more?
Let's wait one more. Wait one more.
All right, we'll do.
All right, we'll jump into this next one. That should help answer that question.
Okay.
Vibration. So vibration is quite different than pulsation. Pulsation is when there's the process pulsing in and out of the pressure gauge, which is causing the needle to jump around. Vibration, and as I kind of mentioned before, is anytime it's mounted on a motor or rotating equipment or something like that. And what that does is it basically just shakes the internals of the gauge. As you can see in these pictures, gauges are made of very tiny parts and pieces. Here's some of the gearing that you can see. Here's one of the link arms, and here's where the board-on tube is welded to the process connection. Some of the visual indicators of failure is that the pointer is not going to return to zero. It seems that a lot of those are. So if you have a pointer that's sitting off zero, there could be a number of reasons, as you guys have learned. It's best to open up the gauge and kind of see what the inside's looking like. That's something that REOTEMP can take care of if you've got an issue, and we can kind of troubleshoot it to see if you guys see what the issue is. The other one is the pointer has fallen off. This could be pulsation or vibration, but this is where your guys' process knowledge would help out. Dust powder inside the case. As these gears rotate or vibrate against each other, they're shaving little metal pieces off, and that dust kind of builds up inside the gauge. If the case is liquid filled, you'll see some of the vibration. If there's heavy vibration, you'll see some of the dust inside the liquid fill. Or the dial screws appear loose or missing. There's little screws on the front of the dial. If those are loose or missing, you can tell if there's vibration because those are actually vibrating out of the screw that they're in, or out of the hole that they're in, and falling off. Internal indicators of failure: rubbing marks on most metal joints. Like I said before, these will wear down. As you can see here, this thing used to be a nice even circle here, but it's been worn down just because of the vibrating against the other linkage. Oblong holes in the linkage holes, or cracks in the structural joints or on stem or board on tube, as you can see in this picture here. We'll kind of get into the solutions of vibration here. So first solution, to kind of answer the question from before, liquid filling is used when there is vibration. it's used to, what it does is essentially it lubricates the internals of the gauge. It keeps those gauges from shaking around, or the internals from shaking around as much as if there was a dry gauge there. And it's just going to help prolong the life of the gauge. Now, a lot of times guys will say, oh, I need to liquid fill my gauge. It's seeing pulsation. That is not the option there, or not the solution there. What happens when a gauge is seeing pulsation and that needle's bouncing around? You can liquid fill it, and it might mitigate that bouncing around quite a bit. But now what that pointer is doing is it's fighting the liquid. It's fighting the weight of the liquid, and that's going to cause the pointer to fall off in a less amount of time than if you were to just leave the gauge dry. The option with the liquid fill is going to be for vibration only. The second mount is if you've got really heavy vibration and liquid filling may not be doing the trick, and you start to see the glycerin cloud up, you're going to want to remote mount it with some sort of a flexible hose or capillary. You can take a gauge, put some sort of a front flange on it, or our process gauges have mounting holes already in them. You can take some capillary, mount it to the process connection, run it back to your gauge, mount the gauge on a wall or a post or something like that away from the process, away from the motor, away from the rotating equipment that's causing that vibration. That's going to extend the life quite a bit. And another option is include the gauge option for DampX. What REOTEMP offers is DampX. It's very similar to the Ashcroft Plus Performance, where the internals are encapsulated in a little silicone potting, and that's going to extend it. Basically, you're getting the vibration reduction without liquid filling the gauge. So you can use a dry gauge to mitigate, if you're afraid of any leaks or anything like that. So DampX is going to be the option there. But DampX is only used for light vibration. If you're seeing heavier vibration, you're going to want to go with a liquid fill. You're going to want to go with a remote mount. And this brings us to our first poll.
All right, let's launch it now and see how good of a job you did, Justin, in explaining everything. Okay. So we'll leave this run for a little bit. And again, just a reminder, if you are in full screen mode, there's a chance you'll need to minimize out of that full screen mode in order to make a selection. So looks like we're getting some responses in here. About 40% of you, about 50 now. It's a not very tight race, which is a good sign, Justin.
All right. What would I see?
All right, getting some more responses in through the question panel. That's good. All right, so I think we've got a pretty good collection right now. I'll close the poll down and then just recap the results. It looks like 75% of the attendees that voted in the poll did get the correct answer of liquid filling. So good job there, Justin.
All right, sounds good. Good job, guys. All right, do we have any more questions through that section, or are we good to go?
Nope, no more questions at this point. So
okay, let's move on here.
All right.
We're going to talk a little bit about heat now. Heat can be a failure of a gauge. Obviously, you see some of these pictures here that the gauges were toasted. Now, these were obviously in some pretty aggressive heat, very high heat and very high temperatures that cause these failures. If there's less heat, some of the visual indicators of failure, the dial may turn yellow or brown. Gauges are only rated up to about 175 degrees. They can handle a little bit higher on the process temp side of things. Depending on the gauge, they're in our catalog with the different temperature ratings. But if the gauge sees higher temps than what it's supposed to, the dial could turn yellow or brown. Or the gauge case, if phenolic, if you're going with a process gauge, could become brittle. Now this one here on the left here was actually in a fire, so it's burnt to a crisp, but as you can see, it became very brittle and just started crumbling apart. Internal indicators of the failure, discoloration of the board on tube, which you're seeing here. It may be black like this, or you could see the metal, metal discolor a little bit. It's a stainless steel, so as it changes color or heats up, it's going to change it. It's going to give it those rainbow colors to it. That could be a visual sign of it. Or there could be a board on tube crack. You'll see right here, this one here had a crack in the board on tube. It's just typically there's a weld here between the process connection and the board on tube, and that weld could be the failure point. as it gets heated up, it's going to cause a failure. It's going to cause that board on tube to kind of, as that pressure is flexing, this is where you're getting all the pressure of that flex is right here at the tip, and that's going to break down the weld, break down the metals there, and cause it to fail. And like I said, this is only in severe cases here, and it is going to be coupled with pulsation, and that's where you're seeing the tube flex back and forth quite a bit. Going to break that down. Two of the things that we can do to isolate the heat, or isolate the heat. First thing is using an isolate the gauge with a steam siphon, a cooling element, or an impulse piping. This right here is a picture of a steam siphon. It's mounted between you have the process gauge right here or the pressure gauge right here, and this would be mounted to your instrument or on your instrument connection. Basically, what this does is this is used for steam. As steam condenses inside here, it's going to create a pool of water, which prevents that steam from getting up into the gauge and heating up the gauge. It's going to stop the gauge from seeing those high temperatures of steam. It's going to be a good option. The second option is going to be a cooling tower, which is this right here, this section of this assembly here. That's going to be a cooling tower. It can be used with or without a diaphragm seal. This is used if you've got more of a hot process, so you've got like a hot oil or something like that inside your process. Inside this cooling tower is a small capillary that runs up to the gauge. Typically, it's about 3 feet long, coiled up in here. And what that does is that keeps the process pressure as the process fluid goes up inside of here. It's going to cool down just by the ambient air, and it can drop the process from 800 degrees here at the process down to 200 degrees up here at the instrument. So it can do quite an effective job of keeping that gauge away from the heat, getting that gauge away in the safe zone. And the second option is adding a diaphragm seal. Now you can use a diaphragm seal by itself, or if there's higher temperatures, you can use a diaphragm seal with a cooling tower to even add further protection. And the diaphragm seal, typically what we'll do is we'll use an all welded design that doesn't have any gasket joints. And what that does, that prevents any gaskets, your Teflon gasket or your Viton gasket. It's going to have a much lower temperature rating than your stainless steel welds are. So we'll go with a gasketless design that has an all welded diaphragm seal that just keeps the gasket out of there and allows you to run at higher temperatures. The next problem is going to be clogging. Clogging is caused by anytime there's any particulates in there. If you've got sand or any kind of process chemicals built up, coagulating inside of there, they're causing a problem. That's going to be that could cause a failure inside the gauge. Like I mentioned before, there's a very small orifice. As I mentioned before as well, gauges have these little restrictor screws in there. If you've got small, fine particulates inside, we can remove the restrictor screw. That's going to work just fine at mitigating that. As you can see, the internal indicators, if these were to get clogged up and the gauge comes back to REOTEMP, we open it up, we pull the restrictor screw out, we can look inside and see if there's just a buildup of whatever your process was, whether it's sand or a flour or any kind of a powdery chemical or anything like that you're measuring. We'll see it built up inside, and that's what's going to cause the gauge to fail. First solution is removing the restrictor screw. Like I mentioned before, if you have any fine particulates in there, removing the restrictor screw is going to work okay because you're opening up that orifice of the gauge a little bit. Or if you've got any liquids that might have small particulates in there, it'll allow those to flow in and out of there evenly and keep the gauge from clogging up. The second option is going to be adding a diaphragm seal. There, right here, we have our flex face diaphragm seal. As you can see, it's mounted real close to the process. So instead of this process getting up inside the transmitter or up inside the gauge, it's gonna prevent that. It's gonna keep it flush here with the piping, and you're gonna prevent any kind of clogging or anything like that. These do come in both a flange style and a threaded style. You may have something that's just threaded down into a little NPT, but it's keeping that process from getting inside the gauge and going to keep the gauge from clogging up, or keeping the transmitter from clogging up as well. You want to go ahead and pull up our second poll?
Yep, absolutely. I will launch it right now. Okay, so our next poll question here to see how good of a job Justin did, which we will be reporting back to Mark. He asked us to do that, so good luck. Which of these is not a sign of clogging? So please just select one here. The pointer is stuck off 0, the pointer has fallen off, or the pointer will not move when pressure is applied. All right. so we've got some responses coming in. About half of you guys have voted, a little bit more now. Some good responses. Give you guys a couple more seconds here. All right, so at this point, about 80% of the respondents have chosen the pointer has fallen off as not a sign of clogging. Is that correct, Justin?
Yes, that would be correct. Yeah.
All right, nice job, everybody.
All right. Did we have any questions to this point?
No questions. So yeah, I'll remind everyone again, please do use that question panel to send anything our way, and we'll make sure to ask Justin.
Okay. All right. We're going to go through a little bit of training on diaphragm seals, how they operate. We kind of went through ways they can be used to mitigate different failure modes or different failures of gauges. This is a cutaway design of an all-welded diaphragm seal. As you can see on a diaphragm seal assembly, the diaphragm portion of it is about 0.003 of an inch thick. It's a very tiny piece of almost what you would call aluminum foil in there. We'll call it a stainless foil. In most cases, it's a stainless steel. It is offered in other materials as well, but as you can see, it's very, very thin. And what that does is that's what's protecting the gauge from any kind of clogging, any kind of corrosive chemicals or anything like that. It's going to prevent those from getting inside the gauge and cause any failures inside there. Lower housing, not all models have a lower housing. In this particular model, it does. It's typically as thick, if not thicker, than the process piping. So it's going to be be able to hold the pressures, the higher pressures. You've got your process connection is either going to be a threaded, flanged, clamped, welded, or inline. So there's many different options, and we're gonna go through a product configurator in a little bit to kind of show you guys some of the different options available. An upper housing is typically not a wetted part, so it's typically, as you can see here, the diaphragm is welded to the upper housing, but it's between the it's got the welded lower housing here welded as well. So the process is going to stop at the diaphragm. It's not going to hit the upper housing, and so typically the upper housing is a lot of times we'll use a stainless steel, but if you've got any corrosive chemicals, you may go with like a Hastelloy or a tantalum lower housing and a tantalum diaphragm or something like that. But you can leave the upper housing as a stainless steel, and that's just to save costs on the metals, the exotic metals. You're not paying for those. And then the instrument connection is on the top. You've got your gauge, transmitter, switch, or whether you're going with a direct mount or a remote capillary, so you can remote mount a transmitter or a gauge with some capillary there. A little bit about how diaphragm seal works. You've got your process fluid on this side. You've got your fill fluid on this side. Every diaphragm seal assembly needs to be filled with a fill fluid on the instrumentation side. And what happens is, as this diaphragm here sees pressure applied from the one side, it's going to translate that translate that pressure to the other side. So as the pressure is applied here, the diaphragm flexes upward and transfers that pressure into the instrumentation, into the gauge, into the transmitter. And what that fill fluid inside of there does is that transfers the fluid accurately. If you were just to have air on the other side of that and not fill your system, what's going to happen is you're just going to compress the air molecules. You might see the needle on the gauge move or your transmitter reading go up, but it isn't going to be accurate because you're compressing the air molecules and you're not getting a good solid reading going through there. One of the things that REOTEMP does, or when you're doing a fill system here, is you evacuate the instrument chamber. You do a full vacuum pull on this line in between the gauge and the diaphragm, and then we fill it with a T-gassed incompressible fill fluid. A lot of times that's a silicone or a glycerin, or you may get into some other halocarbon type fills that are inert and stuff like that. But your most common is going to be your silicone or a glycerin. And what we do is we take all the gases out of those silicones or those glycerins. We pull all the gases out. Then we fill the instrumentation. That way you know that when that diaphragm flexes, it transfers that pressure up into the gauge and it does it accurately. And then this is a hydraulic system. So once you take this apart, once you take the instrumentation apart or take it off the diaphragm seal, you're going to lose that hydraulic system. You're going to lose the silicone fill or the glycerin fill inside, and it's not going to work properly after that. Keys to ideal performance: the diaphragm material. Metallic diaphragms are welded to the seal housing. They're leak tested and highly impervious and durable. They're gonna be your best option when you're choosing a diaphragm material. They're gonna be your highly corrosive materials. They are gonna be leak tested. They're highly impervious. So like as a Teflon or Viton, which we'll show you here. Oh, I guess it comes up with these first. You've got the different materials here. So these are all the different materials we can do diaphragms in. You've got 316, which is common. You've got Hastelloy C, Monel. You've got your Tantalums, Duplex Stainless, Hastelloy B, some of these exotic materials, and those are all used for corrosive applications, different chemical compatibilities with different materials. Teflon and Viton diaphragms that I was kind of mentioning, they are bonded to the seal housing. They're susceptible to leaks. They're a porous material, so you may see some leak. You may see some of the process get through the diaphragm itself and get into the fill fluid. And they are prone to sagging over time, which could, like I mentioned before, it could cause leaks. As the diaphragm or as the housings compress, it's going to compress the Teflon or Viton, and it's going to cause a failure or a leak eventually. Some of the other keys to ideal performance: diaphragm size. Choosing the correct diaphragm size. That diaphragm must be large enough to displace enough fluid to drive the instrument. So essentially, that board-on tube has a spring rate. That diaphragm must be able to drive that gauge enough to flex that board-on tube. So you must have a large enough diaphragm to do that. The smaller the diaphragm, the less displacement you're going to get out of it, and it may not read accurately. Again, you may see some movement of the needle, but it's not going to read accurately. It's not going to be the correct reading. Diaphragm must be sensitive enough to measure the applied pressure. If you've got a small diaphragm and you've got 10 inches of water column going to it, it's not going to transfer that pressure. It's not going to be enough to drive that fluid on the other side. You must have a diaphragm that's going to flex enough. If you apply 10 inches of water column to a large diaphragm, say a 3-inch large diaphragm, it's going to flex a lot more than the little one is. It's going to displace more fluid and be able to move the gauge a little bit better. And then the diaphragm must be sensitive enough to absorb small expansions and contractions of the fill fluid. Anytime if you've got a small diaphragm on there, if the fill fluid on the process side or on the instrument side of things, if the room, say, goes from 70 degrees Fahrenheit up to 100 degrees or 150 degrees because it's in a boiler room or something like that, that fill fluid inside of that is going to expand a little bit, and that diaphragm must be sensitive enough or large enough to accept that. Here we've got a little chart that kind of shows these are all inside of an oven. You've got our thermometer here. You can see it's reading about 120, 122 degrees there, 125 degrees. This 2.2-inch diaphragm here on the left, this is going to be sitting at same temperature, same fill fluid. It's going to have a much larger diaphragm. You can see it's still sitting around 0. On the same temperature, 1.5-inch diaphragm, you can see it's already measuring what, 3-4 psi in there, and that's just because the fill fluid itself has expanded and caused the gauge to read that amount of expansion. And then you see going with a real small diaphragm here, a 0.7-inch diaphragm, it's almost maxed the 15 psi gauge out just in taking it from 70 degrees Fahrenheit up to 122 degrees Fahrenheit. So you can see picking the right diaphragm size for your application is very critical to getting a good accurate reading. A little recap on what we've kind of gone over: how to protect your pressure gauge, the gauge killer, overpressure. The solution is going to be increase your gauge range. That's going to be your best solution for overpressuring. Pulsation, as we saw, there was a couple of different options. If you've got heavy pulsation, your best bet's going to be a diaphragm seal with the Pulse Plus option. Anytime there's vibration, you're going to want to liquid fill it, remote mount it, or use our Dampex if there's minimal amount of vibration, something that it can handle. Anytime there's heat, you're going to want to go with a cooling tower or a diaphragm seal. If you do have an application with heat, let us know what all the specifics are, what the pressures are, what the temperatures are, and we can help you select a good accurate reading instrument. And then corrosion or clogging. Anytime there's corrosion or clogging, your best bet's going to be the diaphragm seal. You could remove the restrictor screw, but that's only if there's small, minute particles inside the process. And that is going to wrap it up for the presentation. Do we have any questions on that section there?
We do. We have a couple of questions here, not just on that section either. So I'll kind of run through these one by one. I guess in terms of diaphragm seals, is there a way for you to generalize or generally say what a typical life expectancy is, or is it maybe entirely dependent on the application?
There are a lot of variables in that. You know, what kind of pressures you're seeing, how often it's going up and down, whether or not there's pulsation, you know, what the chemical is. I mean, we've had diaphragm seals that last 6 months, and people expect that, but you know, in most cases, diaphragm seals last 3, 4, 5. You know, I mean, I'm sure we've got some out there that have lasted 10 years. So, as long as there's no harsh, anything harsh attacking the gauge or the diaphragm seal, it's going to last. It's going to last you a long time. And that's where, if you have specific applications, letting REOTEMP know what those applications are, what the temperatures are, what kind of pulsation you're seeing, what kind of chemicals you're using, we can pick the best solution for the problem.
Okay, perfect. So next question, this kind of goes back to when you were talking about the flush mount option in terms of preventing clogging. So it's somewhat application specific question here, but how do flush mount seals perform in a high temp and high viscosity fluid, such as say asphalt at 400 degrees Fahrenheit?
They would be just fine. 400 degrees Fahrenheit isn't too hot. We can build an assembly with the diaphragm seal up to 800 degrees Fahrenheit. As long as the diaphragm is not as close to the process, as close as possible to the process piping, it would operate just fine. The asphalt would kind of just flow right by it. You wouldn't have any clogging or any issues like that, because there's really no dead legs in there for the asphalt to harden or get cold inside of it. Okay,
perfect. And let us know if there's any follow-up to that question. I got a couple more here, so yeah, please do keep sending them in, and we'll keep running through them. What kind of considerations should we be making when choosing a fill fluid?
Process compatibility is probably number one. If you've got stuff like chlorine or bleach or stuff like that, people will have to go with an inert fill, because you can't have it hit any kind of oils or silicones or anything like that. It could cause fires and explosions and stuff like that, and cause damage to the instrumentation. And then that may cause leaks and other issues. So consideration on fill fluid, the most common is silicone DC200. As long as it's compatible with your with your process, then you're good to go. You know, if you've got you know, in a food application or a food or bev application, if you put a diaphragm seal on there, you're going to want to go with the food grade glycerin. So if there's any leaks or anything like that, or the fill fluid gets into the process, you don't have any contamination that's going to cause any problems. It's a food grade glycerin and traded to food grade specs. So it really just comes down to chemical compatibility on those.
Okay, perfect. And one more here. So is sizing of a diaphragm something that you can do if you're given the process conditions like pressure and temperature?
Oh yeah, that's all we need really, is that. And we even have a little form that I can send that can fill it out, that can show them, you know, all we need is the temperatures, the process connection, what the process is, you know, if there's any problems with clogging or anything like that, we can definitely spec out the best diaphragm seal for the application.
Okay, that's all the questions we have so far. So I think Kevin's got maybe a few words to say here, but if you've got any additional questions, keep them coming in, and we will make sure to get some answers to you.
Okay.
Great. Thank you, Justin. Even though we did a dry run, I feel like I still learned a bunch of stuff that we didn't cover, so appreciate that. Before I get to the last screen, which is going to show what we're going to announce for next week's e-learning, I'd just like to really wrap it up. One thing we didn't get a chance to get to today, and if you look at the screen that you're seeing, is on the far right-hand side, we have a drawing, and that is an output from the REOTEMP configurator tool, and we did go through it during the RTD and thermocouple. But if you'd like any help or just a hand of going through the REOTEMP configurator, it's a great way to build out your own instruments smartly. It will not allow you to create anything that doesn't fit or doesn't make sense, and it will give you again, the drawing. You can tie in and get list price, lead times, and again, certainly we can help you out with more of that if you wish. So thank you again for joining us. We'd love to become involved in any applications you might have, challenging or otherwise. And finally, we're going to get to next week's presentation. Will be, again, we're going to have Corona in, and it's going to be continuous level measurement with radar level transmitters. And we had Norm in last week, I believe, with mag meters. So we're going to have him back based on the response we've gotten. So we look forward to those of you who do want to sit through that to join us next week. Aside from that, once again, thank you very much. We appreciate your support. Stay safe, and we'll talk to you soon. Bye now.